Hi everyone, today we will be discussing two important multivariate techniques used in machine learning: linear discriminant analysis (LDA) and canonical correlation analysis (CCA). Both of these methods are widely used for data analysis and have significant applications in various domains like classification, pattern recognition, and relationship analysis between datasets. I'm Jibin Thomas, and over the course of this seminar, I will take you through the fundamentals of both techniques, explore their mathematical foundations, their applications, and highlight the strengths and weaknesses of each approach. Here is an overview of what we will cover today. First, we will introduce the importance of multivariate analysis and why we use techniques like LDA and CCA in machine learning. Then we will dive into linear discriminant analysis (LDA), covering its basic concepts, mathematical foundation, and applications. Afterward, we will discuss canonical correlation analysis (CCA), its purpose, how it works, and where it's used. Finally, we will compare LDA and CCA and conclude with some insights on choosing between them based on specific use cases. To begin with, let's understand why we need multivariate techniques in machine learning. High-dimensional data. Real-world data often comes with many variables, and analyzing these high-dimensional data sets requires specialized techniques to extract meaningful patterns. Relationships between variables. In many machine learning problems, we need to analyze how variables are related to each other. Multivariate techniques helps us capture and explore these relationships. Improved data interpretation. By using techniques like LDA and CCA, we can reduce dimensionality and make the data more interpretable. LDA and CCA are two powerful methods that helps in different ways. LDA focuses on class separability, while CCA looks at the correlation between two sets of variables. Let's start with linear discriminant analysis (LDA). LDA is primarily a supervised technique used for classification and dimensionality reduction. Its goal is to project high-dimensional data into a lower dimensional space while maintaining class separability. Classification. LDA helps in finding the best line or hyperplane that can separate data points belonging to different classes. Dimensionality reduction. LDA can also reduce the number of dimensions in a dataset while preserving the class structure, which helps improve computational efficiency. A key point to note is that LDA is different from PCA, principal component analysis, in that it focuses on maximizing class separability, whereas PCA focuses on maximizing variance regardless of the class structure. Now let's dive into the mathematics behind LDA. The central idea of LDA is to find a projection that maximizes the between-class scatter while minimizing the within-class scatter. We have a set of data points, each belonging to one of several classes. LDA finds a projection or linear combination of the features that maximizes the distances between the mean of each class while minimizing the variance within each class. Mathematical formulation. The objective function in LDA is the ratio of between-class scatter to within-class scatter. This is given by J of W equal to W raised to T SBW by W raised to T SWW, where W is the projection vector, the direction we are projecting our data onto. SB is the between-class scatter matrix, which represents the variance between the means of different classes. SW is the within-class scatter matrix, which represents the variance within each class. The goal is to find a vector W that maximizes the objective function J of W, which means maximizing the separation between classes while minimizing the spread within each class. So how do we use LDA in practice? Example 1. Face recognition. In facial recognition, LDA can help project high-dimensional images of faces into a lower dimensional space where the classes or different individuals are well separated. This makes it easier to classify new faces. Example 2. Email spam detection. In a spam detection system, the features might include the frequency of certain words or phrases. LDA can help reduce the dimensionality of the feature space and separate spam emails from legitimate ones based on these features. Steps in LDA. First, we need to compute the mean factor for each class. then calculate the within-class scatter and between-class scatter matrices, solve generalized eigenvalue problem to find the projection that maximizes class separation, finally project the data onto the lower dimensional space for classification. Like any method, LDA comes with its strengths and weaknesses. Its advantages are LDA is simple and easy to implement. It provides dimensionality reduction while preserving class separability. It is particularly effective when classes are well separated. Disadvantages are LDA assumes that the data within each class is normally distributed and that all classes share the same covariance matrix. This might not always hold true in real-world scenarios. LDA is sensitive to outliers, as they can significantly affect the mean and covariance estimates. It only works well when classes are linearly separable. If the data is nonlinear, other methods like kernel LDA might be more appropriate. Next, let's talk about canonical correlation analysis (CCA). Unlike LDA, which focuses on separating classes within a single dataset, CCA is used to explore the relationship between two sets of variables. CCA tries to find the linear combinations of two sets of variables that are maximally correlated. For example, in a study comparing test and images, CCA could find combinations of features in the test and features in the image that are highly correlated. CCA is often used in multivariate analysis when you have two sets of variables and want to explore how changes in one set led to changes in the other set. Let's dive into the mathematical formulation of CCA. CCA finds the linear combinations of two sets of variables, say x and y, such that the correlation between these combinations is maximized. P equal to x raised to ty by magnitude of x into magnitude of y, where x and y are the linear combinations of the variables in each set. This process involves finding canonical variables for both sets, maximizing the correlation between the canonical variables from each set, solving the eigenvalue problem for the covariance matrices of x and y to find the linear combinations that maximize the correlation. Applications of CCA are diverse. Multimodal data analysis. In natural language processing, CCA can be used to correlate test data such as word embeddings with image features such as picture data to understand the relationship between the two modalities. Biomedical data. In medical research, CCA can be applied to correlate gene expression data from one dataset with the clinical measurements from another dataset to understand how they are related. Steps in CCA are: compute the covariance matrices for the two sets of variables, find the canonical variables or linear combinations, maximize the correlation between the two sets by solving the eigenvalue problem. Here are some of the strengths and limitations of CCA. Advantages: CCA helps identify the most correlated features across two datasets. It is particularly useful when working with multimodal or datasets where different variables come from different sources. Examples are test and images. Disadvantages: CCA assumes a linear relationship between the two sets of variables, which might not always be the case. It can be computationally expensive when working with large datasets as the dimensionality grows. CCA requires both datasets to be correlated. If there is no correlation, CCA might not provide useful results. Now let's compare LDA and CCA. LDA is primarily used for classification and focuses on maximizing the separability between classes, while CCA is used for exploring the relationship between two datasets. LDA operates on a single dataset with labeled classes, whereas CCA operates on two datasets which may or may not have labels. LDA is more suitable for tasks like face recognition or email classification, while CCA excels in applications like multimodal analysis or correlating genetic and clinical data. In conclusion, LDA is a great tool for classification and dimensionality reduction, particularly when you have labeled data and are trying to separate different classes. CCA is useful when you want to understand the relationship between two datasets and find correlations between their variables. Both methods are powerful, but they are suited for different types of problems. The choice between them depends on the nature of the data and the problem you are trying to solve. Thank you.